Welcome to qnawire.
Chapter 16, problem 108. They're saying that we have a diprotic acid, which is going to be represented as H2 succinate, and it's a biological relevant diprotic acid. And so they gave us our Ka1 and Ka2 values, and they asked us to do some things with the information given. And so for part A, it asks us to determine the pH of a 0.32 molar solution of H2 sucks at 25 degrees Celsius, and only the first dissociation is relevant. So what we first had to do is write out our equation of what's going to happen during this dissociation. So we have H2 sucks, and it dissociates into our H plus and H sucks minus. Remember that all these solutions are aqueous and will be included in our ice table. So now that we do our ice table, we know that we have a starting concentration of 0.32 and then 0 for our products. And then we're going to then subtract from the initial concentration and then add to the other side. For the equilibrium, you just add up your first two rows for the initial and the change column. And so we're going to get 0.32 minus x, and then x and x. So we are already given our Ka value, but we need to remember that Ka is equal to our products over reactants. So our general equation for Ka should be our H plus ion concentration times our H sucks minus concentration all over the H2 sucks concentration. And so since we see that, we can then plug in our values that we have. And since H plus and H sucks minus all have an x, it's just going to be x squared, and then we're going to have 0.32 minus x. And our Ka for Ka1, since we only dissociated it once, is equal to 6.9 times 10 to the negative fifth. And since the 6.9 times 10 to the negative fifth is such a small number compared to our initial concentration, the x in the bottom is negligible and we do not have to include it, which also makes our calculations a little bit easier. So to find our x, we have x squared is equal to the 6.9 times 10 to the negative fifth times 0.32. And then you just take the square root of both sides. And our x ends up being 4.7 times 10 to the negative 3. And so it asks us what is the concentration of, it's asking us to determine the pH of the concentration of 0.32. So this is our x is equal to 4.7 times 10 to the negative 3, and we know that x is equal to our H plus, so to find our pH, we're just going to do the negative log of our x concentration. And when we plug that in, we get the value of 2.33, and that's what our pH is equal to. So that's for the answer for part A. Now for part B, it is asking us to determine the molar concentration of just sucks2 minus. So we're going to have to go through another dissociation of the first equation that we just did with our H sucks. And then we also going to have an initial concentration of H plus, which is going to be the 4.7 times 10 to the negative third. So when we write out this equation, we're going to start off with our H sucks minus, and that's going to then dissociate into our H plus succinate 2 minus. All right, so now since we have this equation, we are going to write our ice table. And like how I said earlier, we're going to just use the same concentration that we had in the final row of that for both our H sucks minus plus H plus. The reason why we're doing this is because it's a continuation of the same problem. It's just asking for the next dissociation constant. So we already created some H plus ions in the first part, and we also created the H sucks minus. So the only thing that was not produced was the sucks2 minus. So now we're then just going to subtract x from the reactant side and then add it to the products. And then for the equilibrium, we just add those two rows up. So we get 4.7 times 10 to negative 3 minus x, and then 4.7 times 10 to negative 3 plus x, and then x. So what we said before, our Ka is equal to our products over reactants. And when we use what our equation is giving us, we should have our H plus concentration times our succinate 2 minus concentration all over our H sux minus concentration. And when we plug in our values that we are given in our equilibrium part, we are getting 4.7 times 10 to negative 3 plus x times x over 4.7 times negative 3 minus x. We also know our Ka2 value is going to be 2.5 times 10 to negative 6. One thing to note here, once again, is that since our Ka2 value is so small in comparison to our initial concentration, those x's are negligible and we don't need to include them. So our new equation is going to be 2.5 times 10 to negative 6 is equal to 4.7 times 10 to negative 3x over 4.7 times 10 to negative 3x. And when you solve for x, we get x is equal to 2.5 times 10 to negative 6. So the question was asking for our molar concentration of Sux2 minus in part A. So our answer is going to be 2.5 times 10 to negative 6, since the succination in equilibrium is just equal to x. All right, so part 3 is the assumption you made in part A justified by the result in part B. So what it's asking is was it right for us to be able to determine the pH from the concentration of H plus in A, and then from the concentration of H plus in B? And to be able to do this, we just need to write down our H plus concentrations from each of those. So for A, we had an H plus concentration of 4.7 times 10 to negative 3 molar, where in B, it was 4.7 times 10 to negative 3 plus x, and our x value in that equation was 2.5 times 10 to negative 6. And so whenever we add this up together, we want our total concentration. So we have 4.7 times 10 to negative third plus 2.5 times 10 to negative 6. And our final concentration for the for our pH in B is equal to that of A, and the reason is because the change during our ice table was so much smaller in our B than it was in our A. And the change was 2.5. So it was almost 1,000 times smaller in change in B than it was in A. So yes, it is justifiable. Due to our A change concentration was greater by 1,000 times than the change in B. So D now asks, will a solution of the salts NaHSC be acidic, neutral, or basic? And we're going to go to another page for this. And we're going to be writing our equation. So we have NaHSUC, and then that's going to dissociate into our Na plus HSUC minus. And so Na does not play a role whenever we are going to be dissociating it again to get a solution. So whenever we do our H sux minus in water, because it's already in a solution salt, we are then going to dissociate that, and we're going to have H sux 2 creates an OH minus. And since we had the OH minus here, we know we're going to have to calculate a KB. for it. And to do that, we easily are just going to do our Ka for our first equation. So Ka1 times Kab is equal to our Kw. And when to find Kb, you're just going to do Kw over Ka. And this is to determine, even though we do produce an OH, which is basic, how basic is the actual solution? And looking at our Ka and Kb values, we can be able to determine that. So we have 1 times 10 to negative 14 over the 6.9 times 10 to negative 5th. And when we plug that into our calculator, we get a Kb of 1.45 times 10 to negative 10. So our Kb value is very small, and then so therefore it is a weak base. So therefore it is going to be acidic. Solution, because it's going to have a small pOH or a large pOH but a big pH. And you can do that by just getting your pKa. So your pKa, your pKb, is equal to the negative log of 1.4 times 10 to the negative 10. And we get a pKb of 9.83. And so to get your pKa, or your pH, it's just equal to 14 minus your pKb. And you get a pH of 4.16. So acidic is the true answer.